All right, so in 5.3, we're going to be talking about what is called the fundamental theorem of calculus. So the fundamental theorem of calculus is what we've been focusing on, and it's what Newton and Leibniz are both credited with discovering to discover calculus. So to help us get to that point, what I want us to do is we're going to get into some groups, and we're going to start off with a U-try, which I know is a little bit different to start with one of those. So let's go ahead and do that. All right, so to find the area of this triangle, we've got some scaffolded steps down here. So the height of our triangle is going to be this height right here, which is going to be our f of x, and our f of x is 1/2 x. So then the base of our triangle is going to be this right here, and the distance from the origin to this point x is going to be x. So the height of our triangle is 1/2 x. The base of our triangle is x. So then the area formula for a triangle is 1/2 base times height. So that gives us that our area as a function of x is 1/2 times our base times our height, which is 1/2 x. Putting all of those together, we get that the area function is 1/4 x squared. So then for any value of x, the area of that triangle is 1/4 x squared. So then we find the derivative of a of x using our power rule. So we get a prime of x is equal to 1/4, and then the derivative of x squared is 2x, which gives us 1/2 x, which is once again equal to f of x. So the point of this exercise was to build up to the crown jewel of our class, which is going to be the Fundamental Theorem of Calculus, Part 1. So there is a Part 2. So each of these each part tells us something different about derivatives and antiderivatives or integrals. So the Fundamental Theorem of Calculus Part 1, often abbreviated as just FTC I, is if f is continuous on a closed interval ab, then the function, and we use capital F of x to represent the antiderivative, same thing we did in 4.9, to be the function, the integral from a to x of f of t dt on the domain a is less than x is less than b is continuous and differentiable on the open interval ab with derivative f prime of x equals f of x. So in a nutshell, what the Fundamental Theorem of Calculus says, if you have an integral of the form, the integral from a to x of some function f of t dt, when you take the derivative of this function, you put the variable, the upper limit of integration, into the function f, and that's your derivative. So basically it says to undo an integral, you're going to use a derivative, and to undo a derivative, you're going to use an integral. So this states that derivatives and integrals are inverse operations of each other. So we're going to do a proof of this. So we're going to go back to first principles. We want to show that the derivative of capital F of x is indeed f prime of x. So we go back to chapter 2, and we know to find the derivative of any function, we take the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Well, that's our difference quotient. But let's take a look at what each of these things are. So if we have f of x plus h, f of x is this integral. So let's draw a picture to help us visualize what's happening. So I have a, I'm going to have x, and then I'm going to have x plus h. So f of x plus h would be the integral from a to x plus h of f of t dt. And we know from the first couple of sections that we've done, this would represent the area underneath the curve f. So here's our curve f. Between our lower limit of integration is a, and our upper limit of integration is x plus h. So if we were to draw that on the graph, that would be this area right here from a to x plus h. So this represents the f of x plus h. We also know that if we had just f of x, that is the integral from a to x of f of t dt. So f of x would be this part right here. So when we highlight that in blue, the yellow and blue turn green. So if we were to subtract f of x plus h, or subtract f of x from f of x plus h, the part that we would subtract off would be the part in green. So f of x plus h is going to, f of x plus h minus f of x is going to be just this piece right here. So if I were to rewrite just the part that's in yellow there as an integral, what would I get? Well, my lower limit of integration would be x, and my upper limit of integration would be the integral from x to x plus h of f of t dt. So this whole thing, f of x plus h minus f of x, is equal to this. So now putting that back in, we would have f prime of x is equal to the limit as h goes to 0 of the integral from x to x plus h of f of t dt, all divided by h. So now by the extreme value theorem, we know, well, on that interval x to x plus h, f of t has both an absolute minimum and an absolute max. So basically, in the picture that I had here, which may or may not be accurate, this would be the absolute minimum, and over here would be the absolute maximum. But it could be somewhere in the middle. We don't know. But somewhere in x and x plus h, it's going to have both an absolute max and an absolute min. So we know that there exists two different inputs in x plus h. Let me draw another picture to help illustrate. So we have f. We'll call that x. And we'll call this x plus h. So then this point right here would be our max. So there's going to be some input, and we'll call that C max. And then here we're going to have a min, and we're going to have C min. And we know that the max is going to be at f of C max, and we know the min is going to be at f of C minimum. So there's some input, and we know that C min and C max are in between the values of x and x plus h by the extreme value theorem. So then, by the estimation theorem that we did last time, we have that we know the area would have to be bigger than this. So if I did the estimation theorem on this picture, the actual area underneath that curve would have to be bigger than the blue rectangle, and the blue rectangle is going to have height C min, and its width is going to be x plus h minus x, so it's going to be h times f of C min is less than or equal to the integral from x to x plus h of f of t dt, which is less than or equal to the height. We have our green rectangle here, which is the max, and we know that that's going to be too big. The width of that rectangle is still h, and the height is going to be f of C max. And we know that that is bigger than that area underneath the red curve. So now, finally, if we divide each of these by h, we're left with f of C min is less than or equal to the integral from x to x plus h. And I'm going to put this as a 1 over h out in front. And I'll leave it in the bottom. All over h of f of t dt, which is then less than or equal to our f of C max. So then this tells us that this piece right here is in between f of C min and f of C max. But the integral from x to x plus h of f of t dt divided by h, that is the derivative if we take the limit as h goes to 0. So now finally, we take note that this is the limit we wish to find. As h goes to 0, this is f prime of x. So if we take the limit as h goes to 0 of all three of these, we'll get that f prime has to be in between these two things. But let's go back to our picture. So in this picture right here, as h goes to 0, what's going to happen here? So as h goes to 0, this point, x plus h, is going to squeeze back here until I have x and x. Well, if that's the case, if these two things squeeze closer and closer and closer together, what's going to happen with C min and C max? Well, when h finally equals 0, C min is going to equal C max, which is going to equal to x. Because the only point between x and x is x. So as h goes to 0, C min goes to x, and C max also goes to x. So then that gives us f of x is less than or equal to the limit as h goes to 0 of the integral from x to x plus h of f of t dt, all divided by h, which is less than or equal to f of x. So by the Squeeze theorem, f prime of x, which is this, has to equal f of x. Because it's less than or equal to f of x, but it's also greater than or equal to f of x. So this shows us then that the derivative of an integral is equal to the integrand evaluated at the upper limit of integration. So first thing, I think it's good for us to see this proof. I will never ask you to do the proof in a million years, but I will ask you to apply the fundamental theorem of calculus to different problems. So the fundamental theorem of calculus part 1 says that the derivative and the integral undo each other. So basically what it says in symbols is the following, that the derivative d dx of the integral from a to x of f of t dt is equal to f of x, or the derivative and the integral cancel out, and we just get back the function f, which is the integrand. So let's do some examples, because there are some fine details that we need to take care of when we do some of these problems. Alright, so example number 1 wants us to find the derivative of g of x. So g of x is equal to the integral from 1 to x of 1 over t dt for x greater than or equal to 0. So this is basically the setup for the fundamental theorem of calculus part 1, right? We have a function defined as an integral. We just have to check, is our function continuous and differentiable on interval a, b? If so, then the derivative is just equal to the integrand evaluated at the upper limit of integration. So by the fundamental theorem of calculus part 1, we have that g prime of x is equal to 1 over x. So we take our upper limit of integration and we replace it in our f So our f of t was 1 over t. So then our derivative is f evaluated at x. So I know what you're thinking. You're like, wait a minute, it's that easy? And the fundamental theorem of calculus says that derivatives and integrals undo each other. So when we take the derivative of an integral, they go away, and we change our variable of integration to the variable that was our upper limit of integration. All right, so let's take a look at example B. So we have h of x equals the integral from 2 to x of t squared sine t dt. So my f of t in this case is t squared sine t. So by the FTC part 1, h prime of x is equal to f of x, which is going to be x squared sine x. All right, let's take a look at our next example. So we want to go ahead and try this one, but let's do a little comparing and contrasting. So in our first two examples, we'll notice that our upper limit of integration was x. Our upper limit of integration was x. But here, our upper limit of integration is 7, and our lower limit of integration is x. Specifically, when we look at the fundamental theorem of calculus, it states that the upper limit of integration has to be x. So we can't immediately apply the fundamental theorem of calculus. So the first thing we want to take note in this example is the FTC part 1 does not apply yet. We must reverse the limits of integration first. Using the properties of integrals. So if we go back to our lesson from last time, we had some properties of integrals from 5.2. Specifically, we had the following property, which was if we have the integral from a to b of f of x, it is the same as the negative of the integral from b to a of f of x. So then we can rewrite j of x using this property where j of x is now equal to the negative of the integral from 7 to x of e to the 3t dt. Now this one is in the form for the fundamental theorem of calculus. So now by the FTC part 1, j prime of x is going to be, well, here I have my f of t is e to the 3t, and I have my minus sign, which I'm going to change the color of to emphasize, and it's going to come down. So j prime of x is going to be this, so negative of f of x, which is going to be negative e to the 3x. So the derivative j prime is negative e to the 3x. So we just have to be a little bit careful. If the upper limit of integration isn't a variable, we have to use properties of integrals to rewrite the integral. Then we can apply the fundamental theorem of calculus part 1. All right, the next one is a U-try for you guys. All right, so in this case, we look at it. Our upper limit of integration is already the x, so check. And then our f of t is going to be the sine of e to the 3t all over the square root of t squared plus 1. So by the fundamental theorem of calculus part 1, f prime of capital F prime of x is equal to f of x, which is going to be sine of e to the 3x all over the square root of x squared plus 1. So basically, we just replace all of the t's in our integrand f of t with x. And that gives us our derivative. All right, so now we need to learn how to combine the fundamental theorem of calculus with all of our other derivative rules. So what were all of the derivative rules that we've learned so far? Well, we have all of our basic derivative rules, and then we have the product rule, quotient rule, and chain rule, right? So let's see how these work when we start mixing in some of our other rules. So example 2, we want to find the derivative. And we notice something immediately. Our upper limit of integration isn't just an x, right? So once again, the fundamental theorem of calculus, part 1, the upper limit of integration is cosine x, not x. So the first thing we need to note is this is function composition. Which suggests we're going to need to use the chain rule. So we'll note that this is, we can write it as, if we have, let me do it this way. If we say u is equal to cosine of x, then we have f of u is equal to the negative of the integral from 2 to u of 1 plus t squared dt. So now this is function composition, and now our upper limit of integration is just a lone variable. So the fundamental theorem of calculus part 1 applies to this, but we're going to have to use the chain rule. So the FTC I now applies, but we must also use the chain rule. So then f prime of x is going to be equal to df du times du dx. So this is the chain rule. And then to find df du, we need to use the Fundamental Theorem of Calculus Part 1. So now we look at df du. So our derivative, we have here our f of t, and it says we are going to replace our variable t with our upper limit of integration, which is u. So don't forget we have this minus sign out in front, so we get negative f of u times du dx, and our du dx is going to be negative sine x. So then here's our f of t, and we put in our u, so we are going to get negative, and then we have 1 plus t squared, so 1 plus t squared, but that's going to be u squared times our negative sine x. But u was cosine. So finally our minus minus makes that plus, so we have 1 plus cosine squared t sine t. And that is our f prime of x. So let's kind of recap, because there was a lot going on in that problem. So we started out, since our upper limit of integration wasn't just a single variable, we had to recognize that the Fundamental Theorem of Calculus Part 1 didn't directly apply. So we recognized that this was function composition, and that we had replaced the upper limit of integration of just x with cosine x. So this was composition, so writing it out, we had u equals cosine x, then f of x, capital F of x, is f of u equals the negative integral from 2 to u of 1 plus t squared dt. So that's our f of t, and we can now use the Fundamental Theorem of Calculus with the chain rule. So the chain rule says that the derivative of f of x is df du du dx. But to take the derivative of df du, this is where we needed to use the Fundamental Theorem of Calculus Part 1. And then the du dx was just our regular derivative. So applying the Fundamental Theorem of Calculus, we replaced all of our t's with u, which gave us this. But then since we were also using the chain rule, we had to replace all of our u's with the cosine of x. I changed all these back to t's. They should have been x's. That is a typo. And that would be our final solution. All right. So I firmly believe the best way to learn how to do these is to do one yourself. So it's now your turn. Let's go ahead and do our u-try for f of x equals the integral from 1 to e to the x of sine t dt. All right, so to do this u-try, we recognize once again that it's function composition. So u is going to be e to the x, then f of u is going to be the integral from 1 to u of sine t dt. So then we recognize that our little f of t is going to be sine t. So then to take our derivative, f prime of x, we have, by the chain rule, we're going to have df du times du dx. So then by the FTC part 1, this is going to be f evaluated at u, so that's FTC 1, times du dx is just going to be e to the x. So then little f evaluated at u is going to be the sine of u times e to the x, which is e to the x times the sine of e to the x. And that will be our derivative. So e to the x times sine e to the x. All right. So let's take a look at C. C is f of x is equal to the integral from sine x to cosine x of t dt. So we look at this and we're like, we've never had one where both limits of integration are a function of x. So this one, we're going to have to use some properties again. So we note the FTC part 1 does not apply. Both limits of integration are functions of x. So we need some properties of integrals again. So we go back to our properties from 5.2. And we've got this property that we're going to use. So we can rewrite the integral can be split into two different integrals. So it says if we have the integral from a to c, so I'm going to call this my a, and I'm going to call this my c, I can split it up into two different integrals with any number I wish in between. So in our case, I'm going to use the number 0 for each of these. So then we can rewrite f of x as the integral from sine x to 0 of t dt plus the integral from 0 to cosine of t dt. And it's worth noting so note I picked 0 but you could choose any constant. So if you wanted to pick 5 or 50 or even 10 million, it doesn't matter. 0 is often just a simple choice to pick, but there's nothing special about it. Any constant would work. Okay, so now we've split this into 2 different things, so we can use our sum rule for derivatives. And the second one is okay. We're going to have to use the chain rule, but here, this one is upside down. So we're going to need to rewrite using our properties of integrals. So if we flip over our limits of integration, if we reverse them, it puts a minus sign out in front. So then we're going to have f of x is equal to the negative of the integral from 0 to sine x of t dt plus the integral from 0 to cosine x of t dt. So now we can get ready to write each of these out using the chain rule. So I'm going to let u equal sine x, and then I'm going to let v equal cosine x. So then finally, we're going to have f prime of x is going to be our derivative of this. If I call this thing g, and I call this thing h, and I have my u and I have my v, I'm going to have dg du times du dx plus dh dv times dv dx. So this is my u, and that's my v. So then dg du is going to be negative, I replace the t with the u, times du dx, which is going to be cosine x, plus dh dv is going to be v times, so I replace the t with just v, times dv dx, which is going to be negative sine x. And then substituting out u and v, I get negative sine x cosine x plus v, which is cosine x times negative sine x. collecting up my like terms, I get -2 sine x cosine x. So after all of that, I get the derivative f prime is -2 sine x cosine x. All right. So now it is your turn. But before I turn you loose, we're going to need to figure out which rules we're going to need to do this. And this one looks a little bit different than the ones we've seen before. So let's go ahead and get started on it. All right, so to use this example, we're going to need to use the product rule. And in our product rule, we're going to have little f is x squared and g is going to be the integral from 0 to e to the x t squared dt. And the product rule is g f prime minus f g prime. So we need to know our derivative. So the derivative of f is easy, that's 2x. But g, we're going to have to use chain rule. So we have our u equals e to the x, and then our g of u is the integral from 0 to u of t squared dt. So then g prime is dg du times du dx, which is going to be u squared times e to the x, and our u is e to the x, so that's e to the x squared times e to the x. So e to the x quantity squared is e to the 2x times e to the x, because a power raised to a power, you multiply the exponents. And then when you multiply two things together with the same base, you add the exponents. So finally, at the end of all of that, we get g prime is e to the 3x. So then the derivative of capital F of x is g f prime plus, I wrote a minus, that's not correct, plus f g prime. So then g f prime gives us the integral from 0 to e to the x of t squared dt times f prime, which is 2x, plus f, which is x squared, times g prime, which is e to the 3x. And that would be our derivative. So the moral of this story is that the fundamental theorem of calculus mixes with all of our normal rules. So product rule, quotient rule, chain rule, any of the rules that we've used before can be mixed up with the fundamental theorem of calculus to have us find more derivatives, essentially. All right, so we're going to move on from the fundamental theorem of calculus part 1 to the fundamental theorem of calculus part 2. So the fundamental theorem of calculus part 2 is nothing short of amazing. So the fundamental theorem of calculus part 2 says if f of x is continuous on the interval AB and f of x is any antiderivative, capital F of x is any antiderivative of f of x on AB, so that is capital F prime of x equals f of x, then the integral from a to b of f of x dx is equal to capital F of b minus f of a. So this is quite astonishing. So this says that the area underneath the curve between a and b of f of x is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. All right, so let's go ahead and try this. So we're going to do example number 3. Last time we calculated the area underneath the curve. So let's do it this new way. So our f of x, so our integrand, f of x is x cubed minus 6x. So we need to find an antiderivative of this polynomial. So what was our rule for finding an antiderivative of a polynomial? We did this back in chapter 4, section 9. So with derivatives, we moved it down in front and subtracted one. With antiderivatives, we add 1 to our exponents, so we get x to the 4th, and then we divide by it by 4. And then we have negative 6x squared, and we divide that by 2, so we get 1/4 x to the 4th minus 3x squared plus an arbitrary constant. So that's our antiderivative. The fundamental theorem of calculus part 2 says that this integral, the integral from 0 to 3 of x cubed minus 6x dx is equal to our antiderivative evaluated at the upper limit minus the lower limit. So it is f of 3 minus f of 0. Well, f of 3 is going to be 1/4 times 3 to the 4th power minus 3 times 3 squared plus c minus f of 0 is 1/4 times 0 to the 4th minus 3 times 0 squared plus c. Well, 0 times anything is 0, so that's 0, that's 0. And we end up with 3 to the 4th power is 81, so 81 over 4 minus 3 squared is 9, 9 times 3 is 27, plus c minus c. So our plus c and our minus c cancel. Make that a fraction over 1, multiply the top and the bottom by 4, and we get 81 minus 108 all over 4, which gives us negative 27 over 4. So the area underneath that curve from 0 to 3 is negative 27 over 4. So let's journey back in time to our last lecture when we did this same problem. So evaluate the definite integral from 0 to 3 of x cubed minus 6x dx. So that was our f of x. We created our partition. We set up our integral by plugging into our Riemann sum. We then used a whole bunch of properties of summations, distributed some things in, split our sums up, pulled out our constants, had some limits. We replaced the sums with what they were equal to. We then played around with it, did some algebra, reduced some things out. Finally, at the end of all of that, we evaluated the limit, and we ended up with 81 over 4 minus 27. Got our common denominator, did the subtraction, and we got negative 27 over 4, which represented that area. So let's see. Doing this problem, I would say that's at least a page worth of work, and that's if we're being generous. Now, by the fundamental theorem of calculus part 1, I was really verbose. We did that entire integral in a very tiny amount of space. So, the area underneath the curve, according to the fundamental theorem of calculus part 2, is given by the antiderivative evaluated at the endpoints of the integral. So one thing we'll notice, when we did our antiderivative, we got our plus c. But since it's f of b minus f of a, we get a plus c and a minus c, and they always will cancel out. So there's some conventions and some notation we want to talk about. So the first one is that note. When we are using the fundamental theorem of calculus part 2, we will always pick the arbitrary constant of integration to be 0. And the reason that we can do that is what I was just talking about, as we saw in this example where I didn't pick it to be 0. No matter what we pick it to be, we're going to add it and subtract it, but positive c minus c is going to give us 0 every time. So since it doesn't matter because it's going to cancel out every time, we might as well just pick it to be 0, which will make our life easier. But if you want to pick it to be 17, go ahead. You'll get the same correct answer in the end. You'll just make yourself work harder. All right, so symbols and some notation. So when we have the integral from a to b of f of x dx, notice, first of all, when we take the integral, that is, we make the antiderivative, we go from lowercase f to capital F. When we do that, both the integral symbol and the differential go away. So when we actually do an integral, both the integral symbol and the differential go away together. So these two things are a pair. So essentially you can't have this without this. So when we do the integral, this also has to disappear. When we do that, we will write capital F of x, and then we'll either write, this is a common notation, a vertical line, and then b and a, which are our limits of integration. Some books and some people will use a right square bracket to do this. Both this and the right square bracket are shorthand notations for the f of b minus f of a. So using that notation then, the fundamental theorem of calculus part 2 is the integral from a to b of f of x dx is equal to f of x evaluated from a to b. So it's just a shorthand notation for writing f of b minus f of a. So when we see it, that's all that it means. So let's go ahead and use this to do a couple of examples. So we wish to evaluate this integral. So we have the integral from 1 to 6 of e to the x dx. So we need an antiderivative of e to the x. So an antiderivative of e to the x is e to the x. and then we evaluate that from 1 to 6. So it's going to be f of b minus f of a, so it's e to the 6th minus e to the 1. So e to the 6th minus e will be our final solution. All right, so one thing I do want to mention is if you log into Blackboard and you look in our blank lecture notes, we're going to have another handout that is going to be very, very handy, and it's just labeled integrals. And it looks something like this. So basically it takes our derivative sheet where we had our function and the derivative that went along with it, but now it's going to add another column for integrals. So as we just used here, we knew that the derivative of e to the x was e to the x. So then, since derivatives and integrals are inverses, the integral of e to the x is also e to the x plus a constant. So this sheet just has a summary of all of our integration, well, not all of them, but it has a summary of our integration rules that go along with our derivative rules. So we can use this to help us out when it comes to taking derivatives and integrals. All right, so back to our regularly scheduled example. We now have, for b, the integral from 0 to 2 pi of cosine x dx. So the integral of cosine x is sine x, and we evaluate that from 0 to 2 pi. So that's going to be the sine of 2 pi minus the sine of 0, which sine of 2 pi is 0, sine of 0 is 0, and that's 0. So it says that the integral from 0 to 2 pi of cosine x dx is equal to 0. Well, why is that the case? How come there is no area underneath the curve? Well, if we think about what cosine looks like, cosine of 0 is 1, and then we have pi, so it goes down, and then it does this, and is down here at 2 pi. So we have our area above, and then we have our area below, and they're equal but opposite, so they add up to 0. Actually, that is a lie picture, huh? Because cosine comes back up like this. So it should look like this. But then these two areas are the same as that area, so they still add up to 0. All right, let's keep going. So C, we wish to find the integral from 1 to e squared of 1 over x dx. So if we look at our integral sheet, we go down, we find 1 over x, and we see that the antiderivative, or the integral of 1 over x dx, is the natural log of the absolute value of x. So our antiderivative is going to be the natural log of the absolute value of x, evaluated from 1 to e squared. So that gives us the natural log of e squared minus the natural log of 1. And I'm dropping the absolute values because they're both positive. E and natural log are inverses, so they cancel out. We get 2 minus, and the natural log of 1 is 0. So the value of that integral is 2. So the area underneath the curve 1 over x between 1 and e squared has area 2. All right, so it's now your turn. So let's go ahead and find the value of this integral, the integral from 0 to pi of x squared plus sine x. All right, so we need to find the antiderivative. So the antiderivative of a polynomial is we add 1 to the exponent and then divide by it. So 2 plus 1 gives us 3, and then we divide by 3. And then the antiderivative of sine is negative cosine. So then we evaluate that from 0 to pi. So then we get pi cubed over 3 minus the cosine of pi minus 0 cubed over 3 minus the cosine of 0. So then simplifying, that is pi cubed over 3. The cosine of pi is minus 1. So a minus minus makes it plus. Minus, well, 0 minus, and the cosine of 0 is a positive 1. So now distributing our minus in, minus minus makes that plus. So finally, at the end, we get pi cubed over 3 plus 2. So the area underneath the curve between 0 and pi of x squared plus sine x is pi cubed over 3 plus 2. All right, so now we've got to ask ourselves a couple of technical questions. So the first question we want, or we need to ask ourselves is, does every function have an antiderivative? It seems that we would really like them to, because if we know an antiderivative, finding the area underneath that curve is super easy, as we just saw, using the fundamental theorem of calculus, compared to the example we did back in 5.2. In 5.3, this makes it super easy. So it turns out that we want to know, does every function f of x have an antiderivative? That is, does there always exist a function capital F of x such that f prime of x equals f of x? And it's very unfortunate, but the answer to this question is no. There exist many functions that do not have elementary antiderivatives. So notice I'm defining elementary antiderivative, and we'll see that in this next example. So example 5 says, find the integral from 1 to 10 of e raised to the x squared dx. So it turns out that this function does not have an elementary antiderivative. And the reason we say elementary antiderivative is we want to avoid this case, because if I said, well, what about f of x equals the integral from 1 to x of e to the t squared dt? Well, by the FTC part 1, the derivative f prime of x is equal to, I just plug x into here, e to the x squared. But this isn't an elementary antiderivative. Because it involves, the antiderivative involves an integral. So that would be us just semantically rewriting something to call it an antiderivative. So what that means is there's no function without an integral symbol that we can write down that is an antiderivative. So we'll have to develop other techniques to do that type of integration. For those of you that are going on to take Calculus 2, well, they'll talk about some of those techniques in that class. Calc 2 is a lot of integration theory. In fact, it is, I would say, about 75% of that class is on doing integrals. Kind of like about how half of this class has been about doing derivatives. All right, so one last thing about integration before we part ways. So if we take a look at example 6, it's the integral from -1 to 1 of 1 over x squared dx. And before we actually do this, let's make a couple of observations. 1 is positive, and x squared is positive, and a positive divided by a positive is positive. So that means this function is always above the x-axis. So then we would know then that its integral would have to be positive. The area underneath the curve would be positive because area above the x-axis is positive. So now we need to find an antiderivative for this. So we need to use algebra to rewrite as, so 1 over x squared, if we bring this up into the numerator, like what we were doing with derivatives, it makes the exponents negative. Then, if we use our antiderivative rule, it says we add 1 to the exponent and divide by it. So the antiderivative is going to be x to the -1 divided by -1, which is negative x to the -1, which rewriting it, putting it back into the denominator, is -1 over x. So then our antiderivative is -1 over x, and we evaluate that from -1 to 1. So that's -1 over 1 minus a -1 over -1. So simplifying, that's a lot of minus signs. So minus minus becomes a plus. And we have -1 minus -1 is -2. And as I noted before, that should really bother us, because that would tell us that the area underneath the curve is negative. But it can't be the case, because we know that function is never negative. So if we draw a graph, we have 1 over x squared. And if I change my window to just go from -1 to +1 and I graph, I get a curve that looks like this. But it tells me that the area underneath that curve is negative. But our graph also tells us something a little bit interesting. So we know right here at x equals 0, we actually have a vertical asymptote. So we want to note the function is not continuous at x equals to 0. So we go back to the very beginning, and for the fundamental theorem of calculus part 2, it says if f of x is continuous on AB and we have an antiderivative, then this is true. So the reason this gave us a lie for the answer is the fundamental theorem of calculus did not apply. So the FTC Part 2 does not apply because the function is not continuous. On the interval -1 to 1. So if we use the fundamental theorem of calculus on an interval where a function is not continuous, it may give us a number, but that number won't be correct. So we have to be a little bit careful. So we can only apply it to continuous functions that have antiderivatives on the appropriate intervals. If we try, it will spit out a number, but the number is nonsense. It doesn't mean anything.